So we're continuing on with our innate immunity, our 4 types. We covered physical and chemical barriers yesterday. That was number 1. And number 2 was the inflammation response, or the inflammatory response. Today we're talking about phagocytes and natural killer cells. Phagocytes might bring your brain back to phagocytosis from wellness and homeostasis. Phagocytosis is known as cell eating. That's right, cell eating. So yeah, there are large granular lymphocytes that kill cells that are infected by viruses, as well as tumor cells, by cell-to-cell contact. I always like to think of it as, instead of cell-to-cell contact, it sounds like hand-to-hand combat, which is kind of like what they do. I'm going to make a lot of fighting analogies here. And this is like, phagocytes and natural killer cells are kind of like your James Bond, who fights off the bad guys, doesn't necessarily target a specific bad guy until the end, but will kill off any bad guys in the process of getting there. Now, if you think of James Bond, you're probably not thinking phagocyte, but you might think of natural killer, because natural killer cells will attack cells that are in your body that are your own cells, but that are infected by viruses, just by coming into close contact with them. So sometimes cells that are infected will lose their antigen or their self-recognition proteins. So these natural killer cells will seek these out, things that they won't attack things that have your self-recognition, that are part of your own body, but they will attack anything else. And therefore they are non-specific. And their numbers don't increase when exposed to a particular antigen, unlike adaptive immunity, which we'll learn about later in this class. So kind of like James Bond again, he's going to fight off the baddies anytime, and he's not going to have the cavalry of police supporting him right away, or at least not until the end of the movie, right? So the numbers of James Bonds don't increase. You have a certain number and they fight off things. Waiting for the last few people to copy that down before I move to the next slide. Okay, so that takes us to protective proteins, number 4. Protective proteins are kind of like plasma proteins. They include those, if you remember, plasma proteins from the cardiovascular system that are in the blood. But they're basically termed complement proteins, and not complement as in, ooh, I love your hair, it's so fetch. Ooh, that's like a 12-year-old reference to Mean Girls. But complement proteins, complement with an E, compla with an E, complement proteins are helpers. They aid in your inflammatory response. So what they do is they make it so that more white blood cells can come to an area. So they sort of clear the road and make things, make more white blood cells arrive at an area so that they can heal and attend to the inflammatory response. So it's kind of like clearing out a road so that more ambulances and paramedics can get to an area. That's sort of your analogy there. But it's not just a helper. There are also these things called a membrane attack complex, which I love. It sounds so like, I don't know, intense. Membrane attack complex. Also short form would be a MAC, M-A-C. A membrane attack complex is so, what's a good word? I want to say a word. I don't think I can say it. Like bad blank. Like so awesome. Because what they do is they will drill holes in the outer shell of viruses or bacteria. And then like, because of the influx of fluids in there, those viruses and bacteria will then explode based on those holes being drilled. So in your textbook, it says, certain other complement proteins join to form a membrane attack complex that produce holes in the surfaces of bacteria and some viruses. Fluids and salts then enter the bacterial or virus, the bacterial cell or the virus to the point that they burst. That's awesome. That's wicked. There's also these things called interferons. You could also call it interferons, but interferons. So these are proteins that are produced by virus-infected cells, so cells of your body that are infected by viruses, sort of as a warning to non-infected cells in the area, so that your body can kill off those infected cells. So those are protective proteins. Obviously, I'm only giving you like one or two notes here because I'm gonna, well, if you already read 13.1 and 13.2 yesterday, like I told you to do for homework, then you already know a little bit about interferons. But if you just study your notes and see membrane attack complex and interferons, you probably need to know more than just those words. So that's why your textbook's going to be helpful for that. Okay, so now we do get to adaptive immunity, which is the second part of our lymphatic system notes. So your subheading is adaptive immunity. So let's say that you are a pathogen of some sort, a deadly, let's not go with a virus, let's go with a bacteria that can make somebody really sick. And you pass all of the first set of innate immunity defenses. So you've passed chemical and physical barriers. You've gone through the nose and got through scot-free. You've gone through the lungs, past the mucociliary apparatus, or you've gone into the stomach and bypassed any pH changes there and more acidic there. So when those innate defenses fail, you now have adaptive defenses that come into play. So adaptive immunity will now be very specific about what is part of your own body, what's considered a self-recognizing thing or a non-self. As indicated by its name, adaptive, it means it adapts to things that happen in your body. So when I talked about natural killer cells and they don't increase when they attack a pathogen and they don't increase in number, that's totally different from this. So when your body encounters something with adaptive immunity, it activates like the whole cavalry. All of the other troops start to come to the area because it's adapting after notifying. If you took American history, it's like that guy said, the British are coming, telling everybody, and then everybody gets all ready. Wow, I just threw an American history reference in grade 11 bio. More you know. Moving on. So it takes about 5 to 7 days for your adaptive immunity to become fully activated, but then it lasts a long time. So that's kind of why when you have a cold, you'll feel some minor symptoms to begin with, and then it'll grow into a bigger curve where you get some full-on cold symptoms, and then eventually you'll get healthier and they'll trail off. Over the course of like 3, 4, or 5 to 7 days, you may still be feeling healthy, but still have some effects, or even at the beginning or the tail end of being sick. But that's where adaptive immunity comes in. Primarily, adaptive defenses depend on those B and T cells, or B and T lymphocytes that we talked about earlier. Now, when we eventually talk about like COVID-19 vaccines on Monday, there are two vaccines that use sort of an old school mentality, which doesn't mean it's a bad thing, where they activate like T cells in order to produce an immune response, which is fine. There are also two newer ones through Pfizer and Moderna that are like new technology. They use mRNA, and we'll talk about that on Monday as well. So it's sort of a new school way of thinking. Both are still going to activate your immune system and help you out, but they just have different approaches to vaccinations. So with adaptive immunity, there are very specific antigen receptors. So if you remember what an antigen is, we talked about it last class, or you might remember it from the cardiovascular system. An antigen is a marker on the surface of a cell, or a bacterial cell, or a virus, or an allergen. But these receptors are on cells, on B and T cells in your body. So they will have receptors that can bind onto those markers that are on viruses or bacterial cells. So it's like a special handshake, or a different shape that matches up, a lock and key fit. So the plasma membrane, the outer covering of a cell, if you remember that from wellness and homeostasis, will have receptor proteins that combine with antigens based on their shape. And that's in a lock and key fit. Okay, So we've got a couple, two or three more slides left here. We're going to move more specifically into the B and T cells, as we've mentioned here in your notes. So something that you should be able to do is distinguish between B and T cells. So it's a classic like compare and contrast B and T cells. You're probably also wondering where they get their names from, and we'll do that as well here. So B cells will give rise to plasma cells, which eventually are the things that produce antibodies. Now, when we say give rise, that's a very like science, university science or medicine or biomedical field term. It just means leading up to or produces. So B cells give rise to plasma cells, and those produce antibodies. Remember, antibodies are those letter Y shaped things that we talked about last class. Antibodies are the things that keep us healthy. They're the things that attack pathogens. So these combine with specific antigens and neutralize them. Neutralize is kind of a fancy term for it kills them. B cells are produced in the bone marrow, and they mature in the bone marrow as well. So that's B for bone marrow. But eventually, after they've matured in the bone marrow, they will migrate elsewhere in the body to your lymph nodes, as well as your spleen, and they'll also circulate in your blood and your lymph as well. So they'll be everywhere. Okay, so I'll move on because the notes will still stay here. It's on the same slide. T cells, unlike B cells, T cells do not produce antibodies. So B cells are the things that eventually produce antibodies, but T cells do not produce antibodies. What T cells will do is they will differentiate or change, like in a fork in the road, into two types of T cells: helper T cells and cytotoxic T cells. So if I took a quick survey or a guess, which one of these two do you think are like the more damaging type of cell? The helper T cell or the cytotoxic T cell? Keenan, based on their name. Yeah, cytotoxic, as opposed to I'm helping. I'm a helper T cell. But they both do a great job to keep us healthy because helper T cells will release chemicals to regulate an immune response. For anybody who does play Call of Duty, it's like they sort of like, I forget that weapon that you sort of like place and then you leave, and then when someone comes in close proximity, it like explodes. What's that thing called? A claymore, yes. It's like a claymore. So that's what helper T cells will do. They'll sort of like, they'll identify some pathogen, virus or bacteria. They'll put down a claymore, then sort of walk away, but still like peer from a distance. And then the virus or bacteria will come by and kablowie. So helper T cells will release those chemicals that'll do that. Cytotoxic T cells will be more like in your face, like cytotoxic T cells attack and kill virus-infected cells and tumor cells. So they'll get in there. Helper T cells will do it more passively though. But they both are very protective for your body. Now, in terms of T cells, they are like B cells that are produced in the bone marrow, but where they mature is in the thymus. So that thymus gland right at the middle of your chest, above your heart, below your throat. So they mature in the thymus. That's where the letter T comes from in T cells. So is it where they're produced or where they mature, where they get their names from? The answer is it's where they mature, because they're both produced in the bone marrow. So that's the difference between B, or similarities as well as B and T cells. So how are they different? Well, the B cells produce antibodies, T cells don't. B cells are produced, well, they're similar in they both are produced in the bone marrow, but they're different because the B cells mature in the bone marrow and then T cells mature in the thymus. And like I said, they're both super helpful in immunity, keeping you healthy. And we'll move on to the next slide, which talks about a little more about adaptive immunity here. Actually, yeah, no, that's fine. So it's adaptive immunity, also known as active immunity. This is actually 13.4 in your textbook, or if you have the white one. So immunity can occur naturally from your body, over the course of time, building up an immunity. There are also things called memory T cells. We didn't talk about those, but memory T cells will remember how to attack something whenever it re-enters your body. And that's a lot of what makes the AstraZeneca and Johnson & Johnson vaccines more old school. They'll rely on your body responding to something called an adenovirus, which you probably encountered at some point in your lifetime. So immunity can occur naturally through infection, or it can be brought about or induced by a medical intervention. Anybody know what we're going to be talking about now? Yeah, vaccines, primarily, right? So there are two types of adaptive immunity. Number one is called active immunity, where you develop antibodies against some antigens naturally. And that's long lasting. That's what any kind of immunization that you've had in grade 9 or before you went into kindergarten, that's what any immunization you've had then has helped you along. Raise your hand if you've had chicken pox before. Yeah, 4 in the class. And for people at home, 4 people raise their hands. That number is much less now because of how far things have come. When I was a kid, pretty much most kids got chicken pox at some point. How many people have had something called rubella? Right, nobody raised their hands. A, because you might not know what the heck I'm talking about, or B, you've never had it, and that's because of an immunization you've had when you were younger. Measles, mumps, rubella, MMR. So active immunity is where you get an injection that has the antigens of a virus or of a virus, and then your body attacks it. So that's very common for like the AstraZeneca vaccine, where you have something that has these spikes of the COVID-19 virus or the coronavirus, and then your body attacks it. But it's non-replicating, so it's not going to actually give you coronavirus. The other method is through passive immunity. Passive immunity is where your body doesn't actually make any antibodies because the injection itself is made up of antibodies. Sorry, I didn't hear your question. Oh, great question. So the question was, how come the AstraZeneca vaccine is causing blood clots? It's a good question. I think that's a major question on people's minds. I believe the video that we will be watching, it's just like there's an 8-minute video and a 4-minute video, explains that. Actually, the 4-minute video explains that very well. And it is, as far as people are noticing, like they're noticing it, but in terms of how often it happens, the reason that it's now been allowed to be used in Canada because it's so statistically insignificant compared to other things that can happen. Like, I think it's, let me try to remember that or look up the number, because I remember seeing an info image about it. There it is. So, right. Statistically, I think this is in the US, but I think, number-wise, it still holds true. The AstraZeneca vaccine, there have been 4 cases in 1 million vaccines to occur for a blood clot. So that's 0.0004% chance. Don't want to deny it because it's a statistic that has happened, but when you compare it to other things, you may have seen it like a birth control pill, which is 0.05 to 0.12, or 500 to 1,200 cases in 1 million. So 500 to 1,200 versus 4. Or if you are a smoker, 1,763 in 1 million. Or if you have COVID, 165,000 in 1 million, or a 16.5% chance. So while I don't want to deny that, they have seen that there have been blood clots, I think the national NACI, what does it stand for? National Advisory Committee on Immunization has basically said, yeah, nobody's died from these blood clots. They've never gone that severe, and people have been treated with, been able to treat the blood clots. They have happened, but they've been so insignificant in terms of numbers that they're comfortable with people getting it, with the AstraZeneca vaccine, not comfortable with people getting blood clots. Okay, one thing I wanted to mention here about active versus passive immunity is The reason they're passive and the reason it's active is because in active immunity, you're getting an antigen that your body is actively making antibodies to attack. So your body is making antibodies. Whereas in passive immunity, the injection is just antibodies. So your body's not actually making them. Your body's just getting antibodies, and it's not copying them or making them. So that doesn't last as long as active immunity. Immunization is a type of active immunity through the use of vaccines. And this statement used to be entirely true, but now with the new onset of the mRNA-based vaccines through Pfizer and Moderna, it's not necessarily 100% here. So a vaccine is typically was a substance that contains an antigen, a marker, if you remember, to which your immune system will respond to. I guess it still does hold true, even for Pfizer and Moderna vaccines. It's just they relate more to mRNA, which I understand that you guys probably don't know a ton about right now. You do cover it really in depth in grade 12 biology, should you continue on with that course. So how does this all work with an immunization or a vaccine? As you probably know, for a grand majority of the vaccines for COVID-19, you need how many shots? 2 over the course of time. Now, they do recommend 3 to 4 weeks for your second shot after, but the National Advisory Committee on Immunizations has now stated last week, very recently, that you can go to 3 to 4 months before having your second vaccine. So that's why in Canada, that's what's happening here. I'm going to continue on to the next slide, assuming everybody has this one. So you're going to draw on the next slide, and we're going to talk about active immunity due to immunizations. Before I switch the screen, I'm going to tell you why you need 2 shots for these 2 vaccines, or for these vaccines. The first one is to just really kickstart your body to have an immune response to those antigens, aka spikes on the surface of a virus. Your body will create antibodies to attack something like that in the future. So it's stockpiling a whole bunch of antibodies. It's trying to make antibodies. So then when you have a second exposure, or that the booster shot, sometimes it's called, your body now is like really into revving up mode and making those antibodies that it can now attack. So any future exposure to an infection or a virus, your body's got it. It's now been trained with creating antibodies. It's been trained to attack that actual virus spike in its actual form. So this is what is shown here. On this graph, you don't have to make it a rectangle or whatever, but on your y-axis, on the left here, is your antibody concentration or number of antibodies that your body has. And on the x-axis is time. So your vaccination occurs here, right near the beginning of time on this graph, and your body will have a primary response, and those letter Y's are antibodies, these red little Y's. So that later, when you are exposed to an infection, your secondary response is a massive amount of troops coming to your defense. Remember in Endgame, if you've never seen Endgame, I'm so sorry, I'm going to ruin the ending of it. But, you know, that was, how many years ago? 2019, 2 years ago. If you've never seen Avengers Endgame, you probably aren't going to be watching it now because it's that massive. You got Captain America at the end fighting Thanos. And then at some point, the whole cavalry comes to save him, and it's the most epic thing ever. That's kind of like what happens in your secondary response. Your backup is there, your crew has come to save you, you're good. So at the bottom, it says primary antibody response. The antibody concentration, or the number of antibodies, rises gradually and peaks up about 2 weeks after vaccination. And that's why they say when you have your first shot of a COVID vaccine, they say about 2 weeks afterwards is when your body is at least ready now to take on things. It's not, it's not like go around licking people's faces. Let's not get out of hand here. That's kind of gross. But your body is now, after 2 weeks, prepared to take on a possible exposure. At the very bottom, it says secondary antibody response. The antibody concentration rises quickly and the response is more intense. And therefore, your antibody concentration will remain higher for longer. So a question from the audience is, can we leave? No, the answer is no. I got a video to show you after this. You cannot go back to bed. So I'm going to give you about 2 more minutes to finish off this diagram and the points below it, and then we'll move on to just sort of a wrap-up video for today. And then I will send you home. Okay, we're almost done here. I'm going to switch screens so that I can show you the video and take out my microphone and plug in the sound as well.
This is the story of the cult favorite, best-selling, waitlist-inducing Always Pan. I created the Always Pan.
An overview of all the major body systems is nice, but something remarkable happens when you explore one body. An overview of all the major body systems is nice, but something remarkable happens when you explore one body system at a time in a bit more depth. And, in our opinion, one of the most fascinating systems of all is the immune system. Why? Because it features cells in your body that work day and night together to protect you from a constant threat of pathogens trying to bring mayhem. And most of the time, you don't even know it. Most of the time. By pathogen, I could mean a lot of things. A lineup, viruses, bacteria, fungi, protists, parasitic worms. We could go on. Your body has external protection against these things, like your skin. We call that a first line of defense because it's the first line against letting these pathogens inside your body. Mucous membranes, too, like the lining of your nose, will keep pathogens from getting inside. This first line of defense is non-specific because it's not selective about what it blocks from getting into your body. But this is all not foolproof, and sometimes they do get in. And when they do, your immune system has all kinds of ways to deal. After all, this is not its first rodeo. So let's say they break through our first line of defense. Well, the second line of defense includes the inflammatory response. To explain it very simply, let's say you step on a sharp stick, and there's some bacteria on that stick, in your foot. The initial damage of this stick into your foot can cause certain types of cells, such as a mast cell, to react. These cells are filled with substances that work with allergic responses and inflammatory responses too. One substance that they contain is histamine. If they are triggered to release histamine, the result is that this will cause blood vessels to dilate, meaning they widen, near the injury. Histamine also contributes to making these blood vessels leakier. The dilation and the leakiness of the blood vessel makes it easier for many types of white blood cells, such as certain types of macrophages, to reach the area. And macrophages do what macrophages do best. They consume the pathogens. Additionally, your body has a complement system. The complement system is not what it sounds like. It basically works to help or complement the actions of the immune system. It can work with non-specific or specific responses. In this situation, the release of complement factors, in this case, can further attract macrophages to the area to consume pathogens. When all this signaling stops, the damaged area can return to normal. The pathogen has been terminated. However, that also was a non-specific response. Who knows what was on that stick? So that takes us to the third line of defense, the specific line of defense. If you had a cold virus spreading through your body, you may need your response to be targeted on that pathogen. Now, as we give our typical notice, the immune system is very complex. We've just been giving some basics, and we're going to continue to do so. But there are a lot of extra details and exceptions that this short video can't go into. We encourage you to explore. Okay, so we mentioned, what if we need a more targeted response? We're moving into something known as adaptive immunity. Sounds fancy. This is a specific response to an antigen. An antigen is something the body recognizes as non-self, and in this case, it is something that would be a part of the pathogen. This adaptive response is going to be the third line of defense, as the first and second line of defense may not have been enough to control the pathogen. We're going to focus on the basics of two adaptive responses, cell-mediated and humoral. Cell-mediated. This involves the cytotoxic T cell. The cytotoxic T cell is a white blood cell that has the ability to destroy cells that have been infected by the pathogen. It does this by releasing signals that causes the infected cell to do apoptosis, which is a type of self-destruct. It can do this by releasing a protein called perforin, which actually causes holes in the cell membrane. This causes water and ions to flow into it and destroys the cell. When cells that have been infected by a pathogen are destroyed, this can also destroy the pathogen, or it can mean the pathogen at least can no longer replicate inside that infected cell. The thing is, for this response to work, you have to activate a cytotoxic T cell. Stimulating a cytotoxic T cell could mean an infected cell presents an antigen from the pathogen that had infected it. The infected cell presents the antigen on its own cell membrane, kind of like a little flag saying, "Hey, I've been infected, and here you go, this is what it is." This activates cytotoxic T cells to bind and release signals that causes the infected cell to perform apoptosis. But there's another way to stimulate cytotoxic T cells too. Remember how macrophages may have been consuming the pathogen? When they do, they process the pathogen, and the antigens from the pathogen are transferred to the macrophage's surface. A white blood cell called the T helper cell can bind. The macrophage will release chemical signals, which then causes the T helper cell to release chemical signals, which then can stimulate cytotoxic T cells. Cytotoxic T cells will be in search of infected cells so they can stop the pathogen, and they will also continue to amplify the immune response. That's the cell-mediated response, simplified. But remember how we mentioned those helper T cells? They're big helpers as they help not only in the cell-mediated response, but they also help in the humoral response. So what happens in the humoral response? In one scenario, a macrophage has consumed a pathogen, and once again, has an antigen from the pathogen on its cell membrane surface. Then it binds a helper T cell. That helper T cell could also stimulate a white blood cell known as a B cell. B cells are white blood cells that have the ability to make something called antibodies. Before I define antibody, can we just take a moment and recognize that there are three words that sound very similar and can involve the immune system. Antigen, which is something that the immune system recognizes as foreign to the body. We've been mentioning that one a lot. Antibiotics are substances that can specifically destroy bacteria. We have a separate video on those. But antibodies are something totally different. Antibodies are proteins, and they tend to be in a Y shape. Antibodies have an antigen binding area where they bind a specific antigen. They will be found in blood, but many antibodies can also be found in mucus, saliva, breast milk, and more. There are different classes of antibodies. For example, IgE can protect against parasitic worms, and it's responsible for a lot of allergic reactions. Antibodies are generally very specific, so there must be an antibody that is able to bind to an antigen. When antibodies bind an antigen, they can deactivate the pathogen by affecting the ability of the pathogen to move, reproduce, or cause harm. The binding can also be like signs telling macrophages, "Here it is, come eat it." So activating B cells causes these antibodies to be produced, and this is part of the humoral response. While B cells can be activated by a T helper cell, they can also be activated by free antigens themselves that they may come in contact with. Now, we do want to mention that both in the humoral and cell-mediated response, there are memory cells. There are memory B cells and memory T cells. These cells keep a memory of the antigen they were exposed to. Memory B cells can activate plasma B cells, which will make antibodies. Memory T cells can activate cytotoxic T cells, which will go after infected cells. The ability to keep a memory is very important, and this is also where vaccines come in. Vaccines can introduce either an inactivated or very weakened pathogen. This means the body does not get the disease itself, but it will launch an immune response. By launching an immune response, there will ultimately be memory immune cells that will be involved in launching an efficient attack if that pathogen is ever encountered in the future. Overall, this immune system that you have, it's pretty incredible. There are entire giant textbooks about this topic alone, and careers dedicated to studying it. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.